Hello, good evening. Today, I, Bharat Suresh, will be presenting my topic of experiential learning, vapor compression refrigeration using Minitab. I'll be doing a simulation of it. Firstly, I'll be describing about the process of vapor compression refrigeration. Vapor compression refrigeration, yeah, vapor compression refrigeration cycle is the most commonly used refrigeration system in domestic, commercial, and industrial applications. It operates on the principle of compressing and expanding a working fluid to transfer heat from a low temperature region to a high temperature region. This process follows the second law of thermodynamics, where heat is absorbed at a lower temperature and rejected at a higher temperature with the help of external work. Components of a vapor compression refrigeration system includes a evaporator, which absorbs heat from the refrigerated space. The process involves a low pressure, low temperature refrigerant entering the evaporant at a saturated liquid vapor mixture. As it absorbs heat, it completely evaporates into a superheated vapor. Superheated vapor at low pressure and temperature is the output. The next component is compressor, which increases the pressure and temperature of the refrigerant vapor. The compressor sucks in the low pressure, low temperature refrigerant vapor from the evaporator and compresses it to high pressure and high temperature. The output is a high pressure, high temperature superheated vapor. Types of compressors include reciprocating compressors, rotary compressors, scroll compressors, centrifugal compressors. The third component is condenser. The function of it is to reject heat to the surrounding environment. The process is that the high pressure, high temperature vapor from the compressor enters the condenser where it releases heat and condenses into a high pressure liquid. Output: high pressure, high temperature subcooled liquid. Location: it is located outside the refrigerant or air conditioning system. Types of condensers include air-cooled condensers, water-cooled condensers, and evaporative condensers. The fourth component is expansion valve or the throttle valve. The main function of it is to reduce the pressure and temperature of the refrigerant. The high pressure liquid refrigerant from the condenser passes through an expansion valve where its pressure drops suddenly, causing some liquid to flash evaporate into a low pressure, low temperature mixture. The output is a low pressure, low temperature liquid vapor mixture. Types of expansion valves include capillary valve, uh, thermal expansion valve, electronic expansion valve. The working principle of a vapor compression refrigeration cycle involves four thermodynamic processes. One as represented on pressure entropy and temperature entropy diagrams, which will be explained using the simulation. Process involves an isentropic compression. Refrigerant enters the compressor as a low pressure superheated vapor. The compressor compresses the vapor, increasing pressure and temperature. The refrigerant exits as a high pressure, high temperature superheated vapor. Step 2 is condensation, which involves an isobaric heat rejection. The refrigerant releases heat to the surroundings. To the surroundings, the refrigerant changes phase from superheated vapor to a high pressure liquid. It exits the condenser as a high pressure subcooled liquid. The third step is expansion, which is a isenthalpic expansion. The refrigerant expands through the expansion valve, causing its pressure and temperature to drop. A part of the liquid evaporates into a vapor, forming a low pressure, low temperature liquid vapor mixture. The fourth step is evaporation, which involves an isobaric heat absorption process. The refrigerant absorbs heat from the surrounding space. It fully evaporates into a low pressure superheated vapor. The cycle repeats as the vapor re-enters the compressor. The advantages and disadvantages are numerous. The advantages include high efficiency compared to absorption refrigeration, compact design, and low maintenance. It is suitable for wide temperature ranges. Fast cooling and high reliability are also good advantages of it. Disadvantages include environmental impact due to refrigerants, compressor noise, and energy consumption. The applications include domestic refrigerators and freezers, air conditioning systems, cold storage and food processing, pharmaceuticals and chemical industries, industrial refrigeration, supermarket, and display freezers. Now, I'll be talking about how we are going to do the simulation of the VCR cycle in Minitab. We are going to be performing a regression analysis. The first step is to enter the data in Minitab. I have already taken values from the thermodynamics lab about the values of the vapor compression refrigeration cycle. These were the values which were obtained. T1, T2, T3, T4, T5, P1, P2 are the input values or the factors, and COP theoretical, COP actual, COP Carnot, COP relative, and tons of refrigeration are all the responses. T1 is the evaporator outlet temperature, T2 is the post compression temperature, T3 is the post condensation temperature, T4 is the post expansion temperature, T5 is the freezer temperature, P1 is the upstream compressor pressure, P2 is the downstream compressor pressure. Response variables includes theoretical COP, actual COP, Carnot COP, relative COP, and ton of refrigeration. I've already, like I said earlier, I have already taken these values from the thermodynamics lab and I've plotted it on Minitab. The next step is to perform a multiple linear regression. This involves going to statistics, choosing regression, choosing and choosing fit regression model. From this we will plot graphs and also plot a regression model between the response variables, between each response individual response variable versus the input factors. As we can see, the first regression analysis which we have obtained is of COP theoretical versus T1, T2, T3, T4, T5, P1 and P2. The regression equation is as follows. The regression equation is given by y is equals to b naught plus beta 1 t1 plus beta 2 t2 plus beta 3 t3 plus beta 4 t4 plus beta 5 t5 plus beta 6 p1 plus beta 7 p2 plus epsilon. This is the regression equation that has been plotted based on the values that we have taken about COP for COP theoretical. The coefficients I have been given. Based on these coefficients, the t value and the p value have been plotted along with the VIF. The model summary has also been plotted by Minitab using the simulation. We have also performed the ANOVA series for this equation. We found the degrees of freedom, the SS, the mean square, the F value, and the P value. Based on that, we have plotted a fits and diagnostics for unusual observations. Similarly, we have performed the same for COP actual versus T1, T2, T3, T4, T5. The COP actual is given by the following equation. Coefficients have been given along with t values, p values, and VIFs. A model summary of the equation has also been made. This is followed by an analysis of variance, which involves giving the degrees of freedom, sum of squares, mean of squares, f values, and p values. Fits and diagnostics for unusual observations have also been given. Similarly, we have performed the same process for COP Carnot versus the input parameters. We've also done that for COP relative versus the input parameters. Next is for ton of refrigeration versus the input parameters. This is followed by showing a graph of the regression analysis between COP theoretical versus the input parameters using a histogram. Then we have performed the same thing for COP actual versus the input parameters, COP Carnot versus the input parameters, and COP relative versus the input parameters. The same process was also repeated for the tons of refrigeration versus the input parameters. Following which, now we'll use the ANOVA method. The two-way ANOVA method in which we are using two factors. We are plotting using two factors against one response variable. In this, first we'll go to statistics, go to ANOVA, general linear model, fit general linear model, select one response variable, select two independent factors in the model. We'll click graphs, and then we'll go to residual plots to check model assumptions. Then we'll click OK to run the analysis. As we can see, we have plotted COP theoretical versus T1, T2, T3, T4, T5, P1 and P2. The, the graph has also been plotted against COP theoretical versus T1 and P1. The normal probability plot has also been plotted along with an histogram. This is followed by creating a general linear model using ANOVA method for COP theoretical versus T2, P2. This is the graph that we have plotted of normal probability plot and histogram. The similar method is followed for COP theoretical versus T3 and T4. Now, we have also performed a one-way ANOVA method of COP theoretical versus T5. This is done by the same method. We go to statistics, we go to ANOVA, and we choose one way. From there, we can choose the response variable as COP theoretical and the input variable as T5. In this, the null hypothesis is that all means are equal. The alternative hypothesis is that not all means are equal. The significance level is taken as 0.05. The factor information is given by factor T5, levels 17, and the values have also been given, which we have already obtained from our equations, from our readings at the thermodynamics lab. The ANOVA method is applied, in which the degrees of freedom is given, the sum of squares, mean of squares, F value and P value. The model summary is plotted based on that, based on which we have also plotted graphs of box plots, and an histogram also, and also a normal probability plot. These values of COP theoretical, COP actual, COP Carnot, and COP relative, and TR were obtained by calculations. COP theoretical was given by T2 divided by T2 minus T1, where we have taken uh, for an actual COP is given by H1 minus H4 divided by H2 minus H1. The TR is given by m dot H1 minus H4 divided by 14,000. These have been plotted using the TS graph and the pH graph for an R134A refrigerant, based on which we have obtained these values, and based on which we have performed a regression analysis and ANOVA model, as well ANOVA model for one way as well as for two ways also, based on which graphs have also been plotted. Now coming to the next portion, which is the optimization method. I have chosen particle swarm optimization for this model, in which I have generated an equation, sorry, a code. This is the code which has been obtained. We have imported NumPy as NP, Pandas as PD, Matplotlib.pyplot as PLT. We have also used PySwarm, which is basically the particle swarm optimization. We have obtained the various, we have uh, given the input of the various parameters or the factors which you are using, along with the various response variables, COP theoretical, COP actual, COP Carnot, COP relative, and tons of refrigeration. Based on this, we have given the feature engineering, which creates additional features that might be useful, including evaporator temperature, condenser temperature, superheat, subcooling, compression ratio. We have also split the data into features and target variables. The polynomial feature transformation for nonlinear relationship has also been coded, following which we create a regression model for each target. Then we train the models. We split data, create and train models, and evaluate models. Following which we code for defining the constraints for optimization, the bounds which represent the operational limits for the refrigeration cycle. Adjust these based on your system's specific constraints. We give lower bounds and the upper bounds. We define the objective function for optimization. We extract parameters, calculate derived features, create a feature vector, predict performance metrics. We want and This is done to basically to maximize COP and TR. So we return negative values since particle swarm optimization minimizes. Using a weighted combination to balance COP and refrigeration capacity is also done. We add constraint to ensure feasible solutions. Condenser outlet temperature should be less than inlet, which is one of the constraints. The other constraints include that subcooling should be positive, superheat should be positive, compression ratio should be greater than 1, minimum temperature lift should be greater than equals to 40, maximum compression ratio is that P2 by P1 should be less than equals to 6. We run the particle swarm optimization method. We extract optimal parameters. Using the codes, we predict the performance at optimal point, and then we print the results. Based on this, we compare it with the original data range, visualize the results, plot original versus optimized parameters, and various other plots such as COP distribution, tons of refrigeration distribution, TS diagram approximation. In addition to this, we are also doing a sensitivity analysis. We perform a sensitivity analysis on each parameter. We create variations of the optimal points, calculate derived features for low value, calculate derived features for high value. We predict performance, calculate sensitivity, and sort by absolute sensitivity. And then we run the sensitivity analysis.